Good day everyone, welcome to the course on biological data analysis and visualization with R. So, in the last class we looked into some of the data organization with R package .IDR. We will continue that discussion and we will talk about another R package which also helps in data organization and data transformation. The package is called DPLYR. Okay, so we will look into some of the functions of this package and we will also do some hands on. Okay, so this is the agenda for this class. So, we will be talking about data transformation with DPLYR packages. So, here is the package link. So, you can find this package again and you can also find in tidyverse. So, if you just have the package tidyverse, DPLYR would be also a part of tidyverse. So, we will again see what are the functions that are available, but we will discuss some of the most useful functions for us. So, here is a list of some of the useful functions and there are many more functions beyond this. So, the first function is called mutate, then you have select, filter, summarize, arrange. Okay. So, this again helps us in kind of reorganizing columns, selecting certain data, etc., or summarize, right? Maybe we want to get some mean value of a column, etc. Okay. We'll illustrate these. So, I will first discuss how these functions work, what are the arguments that you have to give, and then followed by that we will have some hands on and we will actually apply this to a real data set and we will see how these functions work, and this would be very useful as we go into later parts of this course. Okay, so, this is just a very brief intro about DPLYR package. So, this works on tidy data. We have already introduced tidy data and it works with pipes. Okay. So, what are these pipes? So, we will see this sign very soon in the next slide itself that actually is helpful for processing our data. So, here are the pipes that you can see here. This is the percentage percentage greater than percentage sign. There is another sign that we also sometimes use, right? There is a pipe by greater than sign that is also used, but this is the most common one you will see very widely used. So, the first function that we are going to talk about is called mutate. Okay. So, as the name suggests, right? So, you can change data. Okay. So, mutate is usually used applied on a column, right, and you can create a new column, right. So, from your data set, if you have a set of data, if you have a table and multiple features versus the rows are the samples or observations, so you can create a new column from the measures of other columns, or you might want to add a new column from a new data set, new data file, right, that you have just collected. So, that is possible. Here you can see we have this mutate function. So, the data is called noise data. We'll load this data. You have seen this data before, but we'll again explain and I'll show you which data it is. So, we have seen this noise data before, and if the data is called noise data, this is the pipe that will apply and then mutate. So, mutate this noise data and create a column that is whose title is fraction exp sd, right. So, fraction expression sd, right, and then you can say this should be ratio of two columns, values in two columns that already exist in the data. Okay. This is just an example, is a ratio. You can do a lot of these operations, you can say do a lot of things, and you can say create a new column with after whatever value you get. With that value you can create a new column. Then you have this function which says keep all, right, keep all the columns in there. Okay. You can also say keep none, right. So, again these options are there, you can explore them. I will show you when you go to hands on. I will first show you where you can find this list of functions and then we will illustrate these functions on our data. You can also rename variables, right. So, for example, you want to rename the column, right, one column, you do not have to reload the data, you can simply say noise data, again the pipe, right, rename mean expression st is equal to average expression st, right. So, instead of average expression we are saying this is mean expression. Okay. So, it is a similar idea, but in case you want to maybe shorten or maybe the column name was wrong, so you want to correct it. So this is possible with this rename function. The second command that we use is called select. Okay, so this is here are some examples, right, of how we can do this. So what it does, it actually selects a few columns from the data and it creates new variables or tables, right. So if you are selecting multiple columns, you can create a new table out of this, okay, and say create a new table with these columns. Okay, so this is possible and it's very, very easy. So you just say noise data, the pipe, and select, right, select the columns. So here you're saying select the columns, these columns. Okay, so these two columns will be taken out and put in a new table. You can define a new table or use the assignment operator and you get a new table. Or you can also say, right, select this column to this column, right. So this colon means from starting from this column, select till this column. Okay, so this is something possible. You can also say, for example, select not equal to. So if we are seeing, if as long as the column does not match with this term, right, so as long as you are not looking at this feature, include that in the data. Okay, so that's what it means. This is a negative sign, so it means don't select this column. Okay, that's what it means. You can also do something called relocate. Okay, so you can take a column or a feature and say put it after the last column. Okay, so this is something that's also possible. So you can see that you can organize or transform the data frame very, very easily, right, without writing very complex functions. So you can do a lot of things very, very simply with this package. You can do other things as well, right, which are also useful. For example, you can do filtering. Okay, and you can by filtering. So we have seen some functions, right. This select is for selecting rows or selecting columns or features. Here we can filter based, so we can separate out samples, right, or the rows, right. So we are here, the filter function will separate out rows. Okay, so here are the functions. So first is filter, right, and similar notation, noise data filter. Then you can give the condition, right. So this is the column name. If the column value is greater than 1, only select those genes, right. So if for those genes, for those rows where this value is greater than 1, only select those rows. You can also say, for example, distinct for this column. So for this column, for this feature, the genes that have distinct values, only select those rows. Okay, or select those genes. So genes are in the rows here. You can also slice, right. So for example, here is the slice function, right. Again, the notation remains the same. This function is changing. Slice 10 to 15, right. These rows, row 10 to row 15, take that data out, right. Again, you can take a table, right, create a table or a data frame from your original data frame using this function. You can say slide head, right. Take these 5, so slice from head, right, from the top, 5 observations, 5 samples, 5 genes, 5 rows, or you can say slice tail from the last 10 genes or last 5 genes, whatever you like. Okay, so again we can generate new table, right, new data frame from this data set. Okay, so we have seen these functions now, mutate, select, filter. The next one we'll see is kind of creating summary statistics. Okay, so this is not about generating new data frame or subsetting data. Here it will be summary statistics, right. We want some summary of the data, right. So here how it works. So we have noise data. This is again the format is same. It says summarize, okay, and then it says average equals to mean, NA omit. So NA value should be discarded, and DMSD. So for this column, take the mean value and store it in average value. Okay, and this would be the summary. Okay, we'll see in a moment how this looks like. Or you can also say count the features in this column, right. So what are the features you have here? Okay, then we can use the arrange command. Okay, we also have arrange within this package. Okay, so this is how the arrange works. So you can say arrange according to these values of this column, okay, or values of this feature. So here it's number of regulatory TFs, okay. So arrange the values, arrange the genes or arrange the rows according to values of this column. Now this is by default is ascending order, but you can say order arrange this in descending order, right? That's what it descending means here. DESC, descending order, you can arrange, okay. Then you can write a bit more complex functions, right? So you can say noise data group by number of these TFs, transcription factors, okay. So group genes based on the number of transcription factors. So if say two different genes, they show same number of transcription factors, just group them, right, in one group and calculate the mean expression, right. Here is the summarize. So first do this, group by this, then calculate or summarize the data and calculate the mean expression, mean average expression, YPD, right, mean expression of those groups, okay. So this is how this whole thing will work, right. First you create group, then you summarize, right. So you can actually create very complex data transformation commands here using these pipes, okay. All right, so we have discussed a few functions of this package. So let's now go into the package and see their real world applications on a real world data set and what we get, okay. So that's what we are going to do now. So let me first show you the package, okay. So I'm showing you here. This is the part of a tidyverse, part of the tidyverse package, and here are some functions. Again, we discussed some of these functions, but there are many more ways. So here you can actually find this sheet, which actually is a describing the commands that are possible with this within this package. We have discussed only a few of them. As you can see, we have talked about this filter, distinct slices, etc. There are, for example, you have pool, etc. These functions are there. There are other functions as well which we have not talked about. So you can write a lot of these functions on your data frame or table. Okay, so what we will do, we'll actually elaborate these functions now in the hands-on part, and here we have R, right, and this is where we are now, and our console. So first we'll load this package. So I have already installed this package, but if you have not installed, you can simply write install.packages dplyr, right. So this will install the package. We have discussed how to install package, whether it's a normal R package or bioconductor, the method will be slightly different, but we have talked about that. So first what we will do is we will load this noise data, okay. This is something, this data set we have seen already. This is the same data set we have used for many classes. Okay, so this is how we are seeing the first 10 rows and first 8 columns. This is a really huge data set, so I am not writing the whole thing. We can also use the command view, right. We have seen, as you can write view as data, right. So that is possible, right. Okay, so we have seen this data set, we are familiar with this data set. We have this, for example, this average expression here, we have this expression heterogeneity or noise, so that's why we call this noise data set here as well, and then we have some features, genomic features that are compiled here. Okay, so we'll work with this noise data and we'll apply these different functions that we just talked about. Okay, so we'll start with the mutate function. Okay. Okay, so what I will do, perhaps I will create a new data, and new data okay. Maybe it will not show me because okay. So you can see this new column has been added at the end called fraction expression SD, right. This is what we ran, right. This is the command we used. So this is the new column that has been created, which is a ratio of the values in these two columns, okay, and it's saying keep equals to all, right, keep all columns. You can also say maybe keep none, okay, and let's see what happens. Okay, so none means nothing will remain, only this one will be there. Okay, so again, depending on your choice, you can pick. Okay, so we have seen the mutate command. So let's try the rename command now. So as I said, okay, so I'll store this in a new data frame, and we'll have a look. Okay, and here, as you can see, average expression ST has been replaced with mean expression ST, right? Nothing else, right? We have changed this name. Okay, so we can do this mutate and rename. So let's now go into the select part, right, where you can select different things in different ways, which we have talked about, right? So let's first try this select two columns. Okay, and we are creating a new table, right? And let's see what we have in the new table. Okay, so only these columns. You can increase this, of course. Okay, so for example, the gene name, right? And as you can see, the order remains the same, right? So the way you specify this, right, the order, that's how these columns are present. So this is something that you can also use to maybe reorganize some of the columns. Okay, so we can also try the next command, select command, where we say select these columns starting from this average expression YPD to DMST. Okay, not just these two columns, but between whatever data you have between these two columns, pick all of those. Okay, and here are this, right, and it will pick all these columns, right? So including those two columns, average expression YPD and DM underscore ST. Okay, so it has picked these 5 columns, right? So we have 5 columns, it has picked. So you can again do this using this select command. Of course, this is possible to do with other ways as well without this dplyr package, but this makes our life very, very simple. Okay, we can try the other command now, which is the negative command, right? Don't select this column. Okay, all right. So again, let's check what happened. Okay, maybe this will not be visible unless we see a few more, right? So this column was here in the original data. Let's see. Okay, I'll show you in a moment. So this is the original data, noise data. Okay, and this is the STRE column before data box. Okay, and in the new table, this column is gone because we have this, right? So we are not picking that column by using this select command. Okay, and the other command that we are using is the relocate command, as I mentioned, is relocate this column after the last column. Okay, so again, let's see, this column should appear at the end. So as you can see, this column DMYPD class, this appears at the end. Okay, so the original column is gone, right, which was there in the beginning, right, almost in here, right, after DMYPD it was DMYPD class. So this column is gone now. Okay, so these are very simple things that you can do, but nevertheless they actually help us in reorganizing data very, very swiftly. Okay, so let's now try the filter commands. So again, we'll try different things. We have tried mutate, rename, and select commands. Now let's try the filter commands. Okay, so let's try the filter thing. Okay, and one of the things we'll try is this, right? So filter based on value of a column, right? So here we're saying this DM value should be greater than 1. Okay, so filter that data and create a new table. Okay, and what I'll do is I'll simply look at the dimension, otherwise everything else will remain the same, right? So dimension of the noise data, right, 2160, 288, and the dimension of the table. Okay, as you can see, we have reduced the number of genes, right. So we have around 700 genes after the filtering, right. So similarly, you can, let's say, filter based on expression, you can filter based on different things as you like. Okay, so maybe just to give you an example, let's see if we can. Okay, so based on average expression of a gene, I am just filtering, right, and see the dimension. So we have now 1781 genes here. Okay, so we can actually filter based on this. So let's say, let's try maybe. Okay. Okay, so there might be some issues giving. Okay, so it should be the single ampersand, not the double. Okay, so it's a logical AND, right? So that's why it was giving me error. So here is the, we are using a joint filtering, right? We are using two conditions, so that is also possible. And let's see what we get here. Okay, so we have now 623. Right, this is something we have reduced from 2106. So you can put multiple conditions, right, not just one, you can put multiple conditions. Okay, so now let's move on to the next command. Next function that you can apply is called distinct. Okay, so what it's doing is simply giving us the values of the number of regulatory TF column which are distinct, right. So these are unique values, right, they are not redundant values. So what are the unique values that are present here? Okay, and here are the unique values or the distinct values, right, that are there. Okay, of course this is not continuous, and it's also telling me how many are there. So there are 83 distinct values for this number of regulatory TFs. Okay, and the values which are distinct, these are given here under this column. Okay, so you can find this out, and this information could be useful for different applications. So I will urge you to think about this and see how you can apply this information somewhere. Okay. Okay, so we can slice data. As I said, this is for now row. So we talked about select, etc. So select, so is for columns. So here we are use filter, that is for rows, right? We are selecting few genes, and we can also slice data, right? So here, so dimension table. Okay, so we have only 6 rows here, right? So we can slice this, and you can say also slice head, slice tail, etc. I am not illustrating that here again, right? So we can try this slice head, slice tail, just maybe just slice head. Okay, so means top 100, right? So we are taking only 100 genes in the data. Okay. All right, so we have seen these functions. Now how to select genes. Now let's look into the summarize functions and the arrange functions. Okay, so the summarize function, as I said, it will create only summary statistics. Okay, nothing else. We are not rearranging data, but sometimes this could be useful, right? So here is the average value. So average is set as mean of this column, right, values in this column, right, and omit the NA values, right. So if you do not use this NA dot omit, what you will get is the average will be NA. Okay, so that's the, so when you call mean on with NA values, if you do not omit the NA values, it will give you NA as average. So that's why we are using this NA dot omit. So this is something you need to keep in mind. In many cases you will find this. Then try the next command, right, noise data count, right. So what it's saying is it's counting how many genes are there which shows this value of number of regulatory TFs, right. So for example, we have number of regulatory equal to 9, n equals to 9 means there are 9 genes that show that have this 9 number of regulatory TFs. It's not saying like it has the identical TFs, but it's saying the number is same. Okay, so that's the idea. And similarly, you can see, for example, you have 5 genes that have 75 transcription factors each. Okay, so that's kind of the idea. So it takes those distinct values, right, of number of regulatory TFs, and it just simply gives us a count. Okay, so we have seen the summarization statistics, right, summarize and count. Now we'll look into the arrange part. Okay, so here is the arrange function, first arrange function, right. So we are arranging based on this feature. So let's say hit new table dollar. So we are accessing this column in the new table, right, and it's arranging because it's by default it's ascending order. So first genes, right, they are showing values of 0, but we can check, right, for example we can check the tail, right, the end of the column, and you can see this is like this number is 90, 93, etc. So that's why if you want to arrange this in descending order, right, so we'll use this command DSC. We discussed this, right. So by default is ascending, so you have to make, if you want to sort from high to low, then you have to use this descending order, and then we can see head new table, right. So this is now in descending order, high to low, and we can check the tail here. Okay, so tail value is 0. All right, so we have we can now arrange this. So we can arrange data, right. Let's say, let's compare this with right. This is the original data, and let's look into the new table data, right. So if you carefully look at the gene list, right, the original data, the gene was the gene names were sorted, right, alphabetically, but here they are not sorted anymore because they have been sorted based on the number of regulatory TFs, right. So this is a very useful feature, because if you want to sort your table based on one feature, then you can use that feature, and then you can say, okay, we get a reorganized data. Okay, so this could be very, very useful in some cases, right. Maybe you want to pick the top genes, right, for some feature, right. You can do that, and then you can slice the table, right, take the top 100 values, etc. Right. So you can imagine, right, you can combine these different functions that we are talking about and create very powerful functions that can do a lot of very interesting things, right, and useful for your analysis. Okay, so we have talked about, right, how you arrange in descending order. Now you can make it more complex, right. So for example, as I said, we can group by number of regulatory TFs and then summarize the average expression. Okay, so here are the results. So I am storing this. So here first take the noise data, you group by the number of regulatory TFs, right, which we did already, like a count kind of thing, right. So you've seen it's a grouping function, and then we have the summarize, right. Once it has grouped, you summarize the average mean, average expression for this in YPD medium, right. So we have stored this in results. So let's see results. Results is a table, right. Here is the output is a table. Here you can see, right, the here are the number of regulatory TFs, right, transcription factors, and the average expression of those genes that do not have any transcription factor, reported transcription factor, right. So you can see this average expression, right. If you want to see all of this, so maybe you can say n equals to 100, and it will show these all the values, right, and the average expression value, right. So you can see these numbers now, and they vary, right. Of course, this is the average expression, they will vary. You might want to say whether there is any correlation between these numbers or so. We can also test that, right. Okay, it seems that there is no correlation, right. So the number of transcription factor does not matter, right, and you do not have any correlation for on mean expression. Okay, so I think we have covered the comments that we discussed in the presentation, but there are many more, as I said. So please feel free to explore. So I'll go back to the presentation. So here are the references I have already showed you. Right here, here is the reference. You have some documentation which will kind of describe, and I have also shown you the website where you can find this documentation and a summary of the commands that can be used. So to conclude, we have talked about data organization with DPL/R here. We have talked about different functions like select, summarize, mutate. Some of these functions help in choosing specific columns, right, or organizing columns, and some of these functions help in organizing rows or genes or samples, right. And we have also then looked into the applications in hands-on problem. Thank you.